So on page 15, we've got a circular object, and the question is, what happens if you push this object with no friction? What's your first thought to that question? It would slide. It's just like a box on a surface that we dealt with all semester, right? And so it would slide. I like that answer. Okay. Any other thoughts to that question? Yes. It wouldn't rotate. Why not? Okay. Right. And so getting a little preview, static friction, but if we have no friction, then there's nothing to compensate for our push, right? But another thing to think about, does it matter where we push? If I push on the middle, then I provide no torque, it slides, period, right? But if I push above or below, my force has a lever arm and can cause rotation. Now, it won't be the nice non-slip condition, it would be slipping. And so question 2, what's the purpose of this static friction with rolling? Now, if your first thought is, well, how can it be static if it's moving? And so think about a circular object in contact with the surface, right? And so when it rolls nicely, that part of the object that's touching the ground has no relative motion relative to the ground. And so it is at rest for just a split second. Okay, it's relative to the ground, no motion. And so it is static friction, but let's change the way we look at that. What's the purpose of gripping friction? And so just like with our pulley, we said that string goes across the disc and grips to rotate. Well, similar here with a rolling object. You want friction, you want the static gripping friction so that it'll grab it and rotate it, okay? And so I have a little simulation in here. And so let me get that pulled up real quick. And this is strictly, I'll show the ramp one later, but this is strictly with a horizontal surface and it's in a solid cylinder. So what's that shape constant? It doesn't matter. That's not the point here. I do in the green box, one of the settings is your coefficient of friction. So to start, I turned it off. And so this one, the timer begins. I know that it's not moving right now, but when I hit play, it's already in motion. And so it's going to actually trace, I know it's hard to see, but at the bottom of that wheel or disc, there's a green dot. Okay. And we're going to watch that green dot or watch the bottom of the disc in 3, 2, 1. You can kind of watch those divisions on the wheel. What did we notice? Or what did we not see? We didn't see any rotation. There's no friction. So it had an initial velocity. It keeps that same velocity. It's just an object in motion. It stays in motion. There's nothing to change the rotation of that object, right? And so we can add a little bit of friction now. So I'm just going to scroll it up, 0.3. Now this gets interesting. So again, when I hit play, it's already in motion. It encounters a surface that has 0.3 coefficient of friction. In 3, 2, 1. I don't know if you saw that first bit, and it's a little bit indicated there, but pause. Okay. It had just a few little seconds of slipping. It didn't immediately start rotating. And so it had some slipping. Now I'm going to rub my hands together. Slipping means what? Heat loss. So here we are going to start getting into energy. Okay. And so when you have slipping, it takes away some of that energy. And I know you may not be able to make out the numbers, but it says thermal energy created. You started with 25 joules, we lost 8 due to heat. And so there's not as much available left for your linear motion or rotational motion, okay? Now, the orange portion is when you had the non-slip. So that's when it was gripping to rotate. Similar to what I did day 1, I believe, where I wrapped the rope around the water bottle. When I unrolled the cylinder, 1 rotation, how much of the rope descended? A distance equal to the circumference. Remember that? Okay. And so that's our non-slip when things work nicely. And so let me go back to OneNote. And so what's the purpose of static friction, gripping friction with rolling? And so it is to grip, to rotate, but at the end of the day, it's to achieve, or you could say maintain, non-slip. Okay. And we had 3 equations for non-slip. And so your non-slip equations, maybe I write them underneath. It was that, I'll start with displacement. So if you unroll 1 revolution, your linear displacement would equal your angular displacement times radius. And then we saw the same thing previous with our linear velocity, tangent velocity to the disk or whatever, is equal to that angular velocity times radius. Now we haven't done that one in a couple of, y'all, kinetic energy, this one's coming back. This will be the main one we use. But previously with torque, we used this one a lot, right? And so all 3 of these are your non-slip equations. This is the goal. Friction, if it had a mind of its own and had a goal of its own, it wants this to happen. However, sometimes our wheels rotate and they don't go anywhere. If you ventured out when it was the icy days, or if you're like me and grew up on a dirt road and it rained and you went to, move the car, well, if you get stuck in the mud, or if your wheels are rotating, but not moving in the linear direction, by the way, that's also called translating, to move in the linear direction, translating. And so if you rotate, but you're not moving linear, then I don't get any quality. You get that your rotational side of the equation has more than what you need, okay? And so what's friction gonna do? Friction says, oh, I'm rolling too much, I'm rotating too much. And so it's gonna act in a way to decrease omega so that you can increase the linear velocity and you actually go somewhere. It's trying to achieve non-slip. Okay. Again, does friction get a choice? So friction reacts, right? So right now I'm not walking. Is there friction between my shoes and the floor? Yeah. But if I start walking, okay, the more I push back on the earth, is it going to push me more forward? And so friction is not one set number, right? It can grow, grow, grow. And so friction is responding to whatever situation is happening. Well, what about the other option? Okay, what if I'm moving, skidding? So this you may be more familiar with. You slam on the brakes. You move linearly, but not rotate. Okay, this would mean that your linear side is greater than the angular side. And so friction is trying to maintain or achieve that non-slip. Friction, its job is to make that an equal sign. And so what's friction going to do? Friction's going to act in such a way to increase omega, more torque, and decrease that linear velocity. Now, we won't see all the examples today, okay? Hopefully 1, maybe 2 if we're lucky. But friction, don't think, Oh, well, in the fall, boxes that slid, friction was always back. Because I've been using walking as an example. Okay, from September, can't friction be in the positive direction? Can't we have forward friction? Yeah, that's what you get when you walk, right? The grip with the earth propels us forward. Good so far? Okay, the bottom question is basically setting up the next one. So we'll just move on to page 16. And we'll do this one together. Okay, so here they give us some pounds for mass and force. We're going to ignore that. We'll use the SI units, right? And so it gives us the equation. It gives us that constant for the inertia of this tire, okay? Now, by the way, this is probably not a realistic tire. It says the radius is 2 meters. That would mean it's 4 meter sticks high. My dad's a farmer. They got big tires on those tractors. I don't think any are 4 meter sticks high, just FYI. So I think it's an extreme radius, but go with it. Samir? It's going to be 2 column, and the next one's 2 column. Okay. Hopefully you do your best, no matter if it's 1 column or 2 column, right? At the end of the day. Okay. It's about learning physics. Yes. Huh? 11? Oh, scale, we haven't decided it yet. I'm not going to make any promise. The only scale that you can assure yourself, half to pass. So if you earn half the points, that's a minimum pass. Okay. All right, back on topic here. And so it all begins with a force diagram. Draw a force diagram for this. See if you can get it. Okay. Draw your force diagram. Yeah, 1.5 is actually from the ground, okay? That's the assumption we're going to go off. Okay, so hopefully you recognize there's a gravitational force. Now, a little reminder about center of mass. Are we always able to touch the center of mass? No. And so this is an example where the center of mass is going to be at a place that you can't touch. But that's where you draw the gravitational force, or mg, for the object. And again, we want to draw these forces from where they exert. And so normal force is going to be drawn from the surface, and it's going to pass through the center of mass, which that's not really important to us. But the normal force, that middle of the object, is also going to be our axis of rotation. And so both of these forces pass through our fulcrum, our pivot, our hinge. And so normal force is going to provide no torque, and gravity is going to provide no torque. Now, what's probably going to be true about these two forces? They're going to be equal. Okay. So here it doesn't really tell us what direction we're pushing, but the assumption is that we're going to push horizontally. And so the other friction with the surface, it's got to be parallel to the surface. And so these are the only two for, vertical forces. And so Fn is going to balance Fg. We like it when that happens. Next time, whenever we put our object on a ramp, it's not always going to happen that way. And so the last two forces here, we're pushing 1.5 meters, I told you, from the ground. And so if it has a radius of 2, so that's the 2 meter mark. And so 1.5 from the ground is how far from the axis of rotation? 0.5. And so the lever arm for your applied is going to be 0.5 meters. Horizontal force, vertical distance, right? So right there. And then to get friction, we're actually not going to just say, oh, it's to the left. It always is to the left. Always, always, always. Not always with rotating objects. So watch this. I'm changing my approach. I'm going to pause on forces and start talking about torque. So that applied force is causing what direction of torque? Counterclockwise. So again, if you line a force, wrap around the pivot, we are causing a counterclockwise torque, okay? Then I'm going to think, well, friction, it's going to happen at the surface. It can cause either a counterclockwise and go the same direction, or it can go the opposite direction. So if they went the same direction, again, your net torque, you would have a constantly accelerating in one direction. That's not going to be non-slip. And so thinking about torque first, friction's job is to minimize slip. And so friction is going to be a clockwise torque. Notice I figured out the torque before I drew the force. Therefore, friction happens at the point of contact. So look at the bottom of the wheel. What direction of force, what straight line direction would cause a clockwise torque? It's below the pivot. So is this a forward friction or backward friction? It is backward, okay? And if you're like, well, duh, it always is. No, just wait. We're going to have some examples with forward friction, okay? But here to the left, underneath the pivot, that would wrap around the pivot in that clockwise direction, okay? So a little bit of strategy here, figuring out the frictional force direction. Think about the torque needed first. Good deal? Now, what's positive, what's negative? I know the standard is counterclockwise quadrant 1, 2, 3, 4. However, if this is going to rotate while translating is just that linear motion. If it goes to the right, it needs what type of rotation? It needs that clockwise direction. You can think about one rotation. So just here's a little visual for you. Focus on one point. And so if it moves to the right to have a positive displacement from there to there, that point needs to make a clockwise rotation. Okay. So those would be the same consistent direction for this problem. And so I'm going to come in here and say, well, clockwise, I'm going to make friction's torque positive, applied torque will be negative. Okay. All right. Question 1, how far will the tire move in 5 seconds, starting from rest, assuming non-slip? And so assuming it's non-slip, we've already kind of considered that. That's the role of friction. And so we've got our force diagram, F net. There's only one object, and so just MA. And we think back to standard forces. Vertical, we've already said is balance, so it's just the FA to the right minus friction to the left. Net torque equals I alpha. And we said clockwise torque friction minus counterclockwise torque applied. And then we plug our equations in, what we know. So I'll plug in some numbers as we go, like mass, that's the 386. I don't know acceleration, but wouldn't that be helpful to know to find the displacement? So actually, before we solve for displacement, we got to solve for the acceleration first. Applied force, 1,110 is given. Frictional force, did they give it to us? What about the coefficient? Did they give us that? If we fast forward to question 3, what is the minimum coefficient? So that's something that we just have to wait for. So I'm going to keep it as frictional force for now. So I have 2 unknowns. I need 2 equations, so we can do that substitution, system of equations. And so net torque, I, they said is 2/3 mr squared. Alpha, if it's non-slip, then alpha equals, or A equals alpha times R. And so we can plug in alpha equals A over R. And we'll use the full radius since that's the point touching the surface there. And the 2/3 is based on the full radius. And so A over R. And already right there, what do we notice? One set of R's cancels. And then torque of friction is the force of friction, which we don't know, times the lever arm of friction, minus the applied force times its lever arm. And so now, notice, does R cancel out like we did previously? Well, let's look at the lever arms. What's the lever arm for the frictional force? The distance from the force to the axis of rotation. It's also R. And so we can plug in an R right here. But what about the lever arm for the applied force? Is it the full radius? No. And so that second R is not going to cancel out because this one was that 0.5 that we said. So be careful on R canceling. Sometimes all of it cancels, sometimes it doesn't. I'm recording. Yeah, I'm recording. Okay, so let's plug in some numbers here. 2/3 given. Mass 386. Radius, they said it was 2. Again, that's pretty extreme for a tire. And then A is one of the things we don't know. Equals friction, one of the things we don't know. Capital R, the lever arm for friction, is the full radius. And then FA, they said, is that 1,110 times 0.5. And so let's start simplifying the numbers. But at the end, notice we've got 2 unknowns in both equations. We want acceleration to continue our kinematics. So what if we solve the force equation for friction? And then we can plug that into our torque statement. So we'll plug that in right there. Everyone with me? Okay. And so someone grab a calculator. What's 2/3 of 386 times 2? What's that inertia simplification? I get 514.67 equals, now for the force of friction, I'm going to plug in that other equation into, we'll distribute that in a second, And then half of 1,110, 555. And so next algebra, y'all, it's just algebra here, right? And so distribute, and so we get 2,220, and then 386 times 2. What's our next algebraic step? Group in the back, y'all want to focus? Okay. I saw googly eyes a while ago. That doesn't look like physics to me. I'm not calling you out because of one thing I see. It's a collection of things. Okay. In other words, let's pay attention, okay? We have 3 classes after this, and then we test again, whether we like it or not. So the more physics we do, the better. And so combined like terms, I get 1286.67a, and then 2,220 minus 555. I get 1665 there. And so final answer for acceleration, I get about 1.3. Now I just underlined it, but it's actually not our final answer. They didn't ask for acceleration. We got to now go do a little bit of kinematics. Question? So they said you push at 1.5. You're not pushing at the center. You're not pushing at the top. And just so we had to pick somewhere, what is that 1.5 from? I said from the ground, because usually most problems, the ground is 0. So R for the applied force is from your axis of rotation to that line of force. And so the lever arm for the applied force would just be 0.5. Does that make sense? Okay. And so now let's do a little kinematics. Finish that out. And so it said release from rest. Now we know the acceleration. We are looking for how far it travels. And then what else? Oh, they tell us the time, 5 seconds. And so good old second equation. And so 25 times half of 1.3, I get 16.25 meters. So that's a linear displacement. Good deal? And then keep that going. Same tire. How many rotations does this big tire make in 5 seconds? And so again, assuming non-slip, which is what we make the assumption unless told otherwise, then that linear displacement we just found is equal to an angular displacement of the tire times the radius. And so 16.25 meters, we're going to solve for the angular displacement, and the radius is 2 meters. So I showed my units here. Meters is going to cancel. And when we divide that, what do we get? 8.13-ish? Yeah. Unit? Radians. Now that's not what they asked. They said how many rotations. And so final step, what do we got to do to find how many turns that tire makes? Yeah. 1 rotation has 2 pi radians. And so just a reminder, this is where you either use parentheses around 2 pi, or you take that number and then divide it by 6.28. And I get, wait, did I do that right? I got 1.3. Coincidence that the acceleration and number of turns, I would not memorize that. Okay, but 1.3 turns. So 1 full revolution and a little bit more. So that part's pretty old. 3, what is the minimum coefficient of friction that would assure that the tire rotates without slipping? So there's that verbiage again. And a reminder, what kind of friction are we talking about here? Static, gripping, not slipping, okay? And so we just had an equation up above that we solved for friction. We isolated friction already, so I'm just going to copy that down here. And now we know the acceleration. And so I get that the frictional force is 608.2, and that would be newtons. How do we find the coefficient now? There's only one equation that has the coefficient, mu Fn. Now today, we already said Fn equals the gravitational force, but be careful, it doesn't always. We'll go on a ramp next class, and it doesn't equal mg. And so the mass, 386 times 10. And so mu equals our frictional force divided by, and I get about 0.15. No unit, because Newton over Newton. And if you remember, the coefficient is 99% of the time less than 1. Good deal? Okay, so we did all that with torque. We didn't do any of it with energy, and that's okay. The last example we're going to take a look at, I actually have a demo video. And so I don't have a good ramp like Mr. Dr. Lewin does. By the way, this is a retired MIT professor. He has a lot of videos on YouTube. This one is not an hour long. And if you're watching this video, I'll have the separate link. So I'm not going to zoom video, it glitches. But on page 19, we're going to have a race of different objects, okay? Now, by the way, AP will usually throw a box up there as well to compare it with the old box. No rotation, just linear motion, okay? So have a race. We've got spheres. We've got a hoop here. He's going to have some disc cylinders, okay? And so my ramp is not very good. I don't have equal mass, different other factors like he does. So I have these rotating objects, but it's not as good in terms of comparison. And so let me pull up the video